we explicitly said that we would not allow repetition when dealing with our permutations, but there are times when that is probably a bit too restrictive. So the key idea when dealing with repetitions is to determine how many times we overcounted an occurrence. In this case, we'll pretend that there are no repetitions and count how many times we overrepresented what should have been a single item. We'll then use that information to correct what our count should be. Now, this is a useful tool to have in your tool belt anyway, but this is the first time that we're going to use it. So as written, this probably isn't super clear, and so let's set up an example to see what we mean. Let's suppose there are three brothers, Fred, George, and Ron, and they're in trouble with the law. Now, Fred and George are identical twins, but luckily, they are wearing different colored hats, and this will allow us to distinguish them. So, how many ways are there of setting the police line up? And then, if we make them remove their hats, how many ways are there of doing the police line? So let's let F be Fred, let's let G be George, and let's let R be Ron. So with their hats on, the twins can be distinguished. That means that we have pick three ways of creating the police lineup. And let's write these out. Now I'm going to write them out in particular in a very suggestive manner, as you'll see in a second. Okay, so there are 6 ways. And if we now make the twins remove their hats, they become completely indistinguishable. So let's let T indicate twin, since we don't know which brother is which, and let's rewrite out the list above. Okay, so notice that the entries in each column are the same, which is because I wrote each column such that the only difference between entries was to switch the twins. Thus, the twins being the same, there are now only 3 ways of arranging the lineup. So where does this number 3 come from, and how can we generalize this to other cases? Well, TTR is represented twice in our original list above, and there's nothing special about this element, right? Everything is represented twice. So having overcounted everything by exactly 2, that gives us 6 divided by 2 equals 3 total unique elements. So what if there are 3 repeated elements? What would we divide by then? To see this pattern, let's repeat the above argument, but this time let's assume the family has found their long-lost sibling Parker. Now, Fred, George, and Parker are a set of identical triplets. So I don't want to write out all 24 elements, so instead let's kind of pick one representation. And in particular, let's look at the case when the triplets are the first 3 people in the lineup and Ron is last, right where he belongs. Now I'm going to make a little table here so we can see what's happening. Now, Ron is always going to be last, so the only interesting thing is what is happening in the first 3 columns here, like this. So with triplets, we overcounted TTTR by 6. And the number 6 arises because it's the number of ways of arranging each of the triplets. That's 3 factorial ways. So in the case of the 4 brothers, including Ron, there would be 4 pick 4 over 3 pick 3, or 4 ways of picking the lineup. Okay, so in general, the way this works, let's say you're given n objects and you know that k of them are distinct. For each of those distinct objects, let's say that there are n sub I of them, then the total number of possible permutations of these n objects is as follows. Here, the numerator is counting the total permutations if we could distinguish every single object, and the denominator is counting the number of times that we've overrepresented each object. Okay, so for another example, let's do the following. Let's say you have 11 students, and you want to divide them into 3 breakout rooms. Now, breakout room A holds 5 students, room B holds 4 students, room C only holds 2. How many ways are there of sending the students to each of the rooms? Now, to solve this, we're actually going to do the opposite, and we're going to assign rooms to students, not students to rooms. Let's start out by numbering our students from 1 to 11, like so. And beneath each student, I'm going to indicate which room I'm assigning them to. And this, of course, is just one possible example. So if we think about this, we see that this problem is equivalent to asking, well, how many possible unique arrangements are there consisting of 5 A's, 4 B's, and 2 C's? And, well, that just makes this a repeated permutation problem. There are n equals 11 letters, there are 5 A's, 4 B's, and 2 C's. So if we take everything and we plug it into our formula, that gives us 11 factorial over 5 factorial, 4 factorial, 2 factorial, and we're done.